I'm so glad you found your way here. Right now, in this very moment, you're already traveling through space at 67,000 miles per hour, orbiting our sun as Earth carries you through the galaxy. You'll discover how future explorers will leave our planet's embrace and understand why every human who ventures into space becomes part of something infinitely larger than themselves. Welcome to Sleepless Scientist Night. Wherever you are right now, perhaps imagining distant worlds or simply feeling the quiet pull of sleep, allow yourself to rest in this moment of cosmic possibility. We'll drift through 100 space facts about humanity's next great journey. From spacecraft being built this very year, to minds preparing for the longest voyage ever attempted, to the moment when standing on another world becomes as natural as breathing. These quiet journeys through space create a cosmic community of peaceful minds. Feel free to like and subscribe or share a thought down in the comments. It helps others find their way here too, one sleepy soul at a time. It means the universe to us. Settle deeper into your pillows now. Let your shoulders drop, your breathing slow and steady. You don't need to hold on to any of this cosmic knowledge. Just feel that peaceful heaviness spreading through you, like you're floating weightless in the vast, silent darkness between stars, drifting gently towards sleep. Close your eyes and breathe deeply. You're floating where starlight paints pathways through infinite space. Let your mind drift with cosmic silence. And now we begin. Humans are returning to the moon in April 2026. After more than 50 years since the last human walked on lunar soil, 4 astronauts will circle the moon aboard a spacecraft called Orion as part of NASA's Artemis 2 mission. Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian astronaut Jeremy Hansen have spent years preparing for this 10-day journey. The crew named their spacecraft Integrity, a word that captures the trust and dedication of thousands who made this moment possible. Right now, in November 2025, the massive Space Launch System rocket stands assembled inside Kennedy Space Center's Vehicle Assembly Building. The European Space Agency's service module will provide power, water, and breathable air during the voyage. This isn't just a test flight. It's humanity's first step toward living and working beyond Earth's protective embrace, preparing the way for missions to Mars and settlements among the stars. The rocket that will carry these astronauts generates nearly 9 million pounds of thrust at liftoff. To put that in perspective, that's enough force to lift a spacecraft weighing millions of pounds away from Earth's gravity. 4 RS-25 engines, each a masterpiece of engineering originally designed for the Space Shuttle program, work in harmony with 2 massive solid rocket boosters. When they ignite, the deep rumble travels for miles, a steady sound that echoes across the distance like slow rolling waves, felt more than heard as a gentle presence in the air. The rocket stands about 400 feet tall, roughly the height of a 40-story building, gleaming white against the Florida sky. Every bolt, every weld, every line of code represents years of testing and refinement. Soon, this enormous machine will push humans farther from Earth than anyone has traveled since 1972, opening a pathway that future generations will follow to distant worlds. By mid-2027, humans plan to walk on the moon again. Artemis 3 will carry astronauts to the lunar South Pole, a region never before visited by humans, where permanently shadowed craters hold ancient ice and sunlit peaks offer nearly constant solar power. SpaceX's Starship, modified as a lunar lander, will carry 2 astronauts from orbit down to the surface, while 2 others wait above. The South Pole's terrain presents unique challenges. Deep craters and towering peaks create extreme light and shadow, with temperatures swinging from boiling hot in sunlight to hundreds of degrees below zero in darkness. Yet this challenging environment also holds valuable resources. Water ice in those shadowed craters could be split into hydrogen and oxygen, providing rocket fuel and air for future missions. The astronauts will spend nearly a week on the surface, longer than any Apollo mission, testing technologies and gathering knowledge that will make sustained lunar presence possible. Future moon missions will establish a permanent human presence called the Lunar Gateway. This small space station will orbit the moon, serving as a staging point for surface missions and deep space exploration. Unlike the International Space Station, which circles Earth every 90 minutes, the Gateway will take about a week to complete one lunar orbit, following a unique path that requires minimal fuel to maintain. The station will include living quarters, laboratories, and docking ports for visiting spacecraft. Astronauts might spend months aboard the Gateway between surface missions, studying the moon, observing Earth, and testing technologies for the journey to Mars. The Gateway represents a fundamental shift in human space exploration. Not just visiting space, but living there, establishing infrastructure that makes the moon a waypoint rather than a destination, a place to pause before journeying farther into the cosmos. Mars missions could begin as early as 2026 with uncrewed spacecraft. SpaceX has announced plans to send Starship vehicles to Mars during the 2026 to 2027 launch window, when Earth and Mars align favorably for interplanetary travel. These first missions will be robotic, testing the spacecraft's ability to enter the Martian atmosphere, descend through thin air, and land intact on the red planet's surface. Each mission will carry equipment needed to establish infrastructure, solar panels, habitat modules, resource extraction systems that could produce fuel and oxygen from Mars's atmosphere and soil. Success with these uncrewed missions would pave the way for human landings as soon as 2028 or 2029, though 2031 might be more realistic. The spacecraft that makes this journey will be the largest ever to travel between worlds, carrying enough equipment to begin transforming Mars from an alien landscape into humanity's second home, one careful step at a time. The journey to Mars takes approximately 7 months, following a curved path through interplanetary space that covers somewhere between 140 and 300 million miles, depending on where the planets are in their orbits. Unlike the Moon, which sits just 3 days away, Mars missions must wait for optimal launch windows that occur only every 26 months when the planets align. During the journey, astronauts will live in a confined spacecraft, watching Earth shrink to a pale blue dot behind them, while Mars slowly grows from a reddish star to a visible world ahead. They'll experience a new kind of distance. Radio signals take up to 20 minutes to travel between Earth and Mars, making conversations unfold slowly, like letters exchanged across a vast ocean. The spacecraft will cruise through deep space, where the sun appears smaller and dimmer than we see from Earth. For 7 months, home will be a vessel carrying the hopes and dreams of an entire species toward a distant shore. SpaceX's Starship stands over 390 feet tall and is designed to carry more than 100 metric tons to Mars, a capacity that will be tested in upcoming missions as the vehicle continues development. Its design emphasizes reusability. Both the Super Heavy booster and the Starship spacecraft are built to fly multiple missions, dramatically reducing the cost of space travel. The spacecraft's stainless steel construction provides durability and heat resistance, able to withstand the intense heating of atmospheric re-entry. Its Raptor engines burn liquid methane and oxygen, propellants that can potentially be manufactured on Mars using local resources, making the return journey possible. The vehicle's interior can be configured for cargo, crew quarters, or scientific laboratories depending on the mission. Starship represents a new philosophy in spaceflight, building vehicles like airliners, meant to fly often and reliably, making space travel routine rather than extraordinary. NASA's 2025 astronaut candidate class is training right now for future deep space missions. Selected from more than 8,000 applicants, this diverse group includes military test pilots, engineers, a physician, and a geologist. Lauren Edgar worked on the Curiosity Mars rover and the Artemis 3 science team. bringing expertise in understanding planetary geology. They're learning Russian to communicate with international partners, studying spacecraft systems until every switch and procedure becomes second nature, training underwater to simulate spacewalks, and preparing their bodies and minds for the unique challenges of life beyond Earth. These candidates won't fly immediately. They'll spend nearly 2 years in training before becoming eligible for missions. But by the time they're ready, opportunities will include the Moon, Mars, and destinations we're only beginning to imagine. Spacecraft traveling to Mars must carry everything needed for the return journey, or manufacture it there. One promising approach uses Mars's atmosphere, which is 95% carbon dioxide, to create rocket fuel through chemical processes. By combining atmospheric CO2 with hydrogen brought from Earth, machines could produce methane and oxygen, the exact propellants Starship uses. This process, called in situ resource utilization, would eliminate the need to carry return fuel from Earth, dramatically reducing mission mass and cost. Similar techniques could extract water from Martian ice, then split it into hydrogen and oxygen for breathing, drinking, and fuel. The Martian soil itself contains useful materials, iron, aluminum, silicon, that could be processed into construction materials and solar panels. These technologies transform Mars from a destination requiring constant resupply into a place where humans could become increasingly self-sufficient. By 2030, NASA envisions a sustained human presence on the Moon supporting missions to Mars. The Artemis program isn't about planting flags and leaving footprints. It's about establishing infrastructure that makes lunar operations routine. Habitats will provide shelter from radiation and temperature extremes. Rovers will explore and transport supplies. Mining equipment will extract water ice and minerals. Solar panels and perhaps nuclear reactors will generate power. All of this serves as practice for Mars, which presents similar challenges but at greater distance and with fewer options for emergency return. The Moon becomes humanity's training ground, a place to learn how to live off-world while still close enough to home for help to arrive in days rather than months. Each lesson learned on the Moon's surface brings Mars colonization closer to reality. Deep space habitats must protect astronauts from radiation, unlike anything experienced on Earth. Beyond Earth's magnetic field and atmosphere, space is filled with high-energy particles from the Sun and distant cosmic sources. A 6-month mission to the International Space Station exposes astronauts to radiation equivalent to about 50 to 100 chest X-rays. A round trip to Mars, including time on the surface, could expose crew to radiation equivalent to over 600 chest X-rays. This level of exposure presents health considerations that researchers are carefully studying. Understanding how the body responds helps develop protective measures for future travelers. Spacecraft designers are exploring various shielding approaches, water-filled walls that provide both protection and storage, hydrogen-rich materials that scatter harmful particles, even the spacecraft's fuel tanks positioned strategically to shield crew quarters. Careful design and trip planning during periods of lower solar activity can minimize exposure. Artificial gravity might solve many problems of long-duration spaceflight. One proposed design involves rotating spacecraft, spinning slowly to create centrifugal force that mimics gravity's pull. A rotating habitat several hundred feet in diameter, spinning at a carefully calculated rate, could produce artificial gravity for its inhabitants. The larger the diameter and faster the spin, the stronger the gravity effect. Though spinning too fast creates disorienting sensations, engineers are studying designs that balance these factors to create comfortable living spaces. Astronauts would live and work in rotating sections, experiencing normal up and down, reducing muscle and bone loss, preventing fluid shifts that cause vision problems, maintaining cardiovascular health. The engineering challenges are significant. rotating massive structures in space, transferring between rotating and non-rotating sections, managing the gyroscopic effects that affect spacecraft maneuvering. But artificial gravity might prove essential for healthy travel to Mars and beyond. The Lunar Gateway will include an international habitat module built by Japan and Europe. This pressurized living space will provide sleeping quarters, kitchen facilities, bathroom and hygiene systems, and work areas for science and spacecraft operations. Large windows will offer views of the Moon's surface passing below and Earth hanging in the black sky above. The module's life support systems will recycle air and water with extraordinary efficiency. Every breath exhaled, every drop of water used for washing will be captured, purified, and reused. Nothing can be wasted when resupply comes only every few months. The habitat will also serve as a safe haven during solar storms when radiation levels spike. Thick walls and strategic shielding will create a protected area where crew can wait out the storm, perhaps for several days, before returning to normal operations. Mars missions will likely establish habitats partially underground to protect against radiation. The Martian atmosphere is too thin to provide meaningful shielding. Surface radiation levels are hundreds of times higher than on Earth. Burying habitats under several feet of Martian soil would provide natural protection while maintaining access to the surface through airlocks and windows. Some designs envision inflatable habitats deployed in natural caves or lava tubes, geological formations that offer ready-made protection. Others propose using autonomous robots and 3D printing technology to build structures from Martian concrete before humans arrive, with thick walls and minimal windows. Living underground might sound confining, but creative habitat design could provide comfortable, even inspiring spaces, high ceilings, interior gardens, artistic lighting that mimics natural day and night cycles. Future space travelers will grow food during their journeys, transforming spacecraft into gardens among the stars. NASA has successfully grown lettuce, radishes, chili peppers, and other vegetables aboard the International Space Station, proving plants can complete their life cycles in microgravity. For Mars missions lasting years, fresh food becomes essential, not just for nutrition, but for psychological well-being, providing variety in diet, meaningful work tending growing things, and the comfort of living greenery in an artificial environment. Advanced growing systems use LED lights tuned to wavelengths plants need most. Aeroponic or hydroponic systems that deliver water and nutrients directly to roots without soil, and careful environmental control of temperature, humidity, and carbon dioxide levels. The plants also help recycle air, absorbing carbon dioxide exhaled by the crew and releasing oxygen. Spacecraft heading to Mars will need nuclear power systems in addition to solar panels. As spacecraft travel farther from the Sun, solar power becomes less effective. Sunlight at Mars is only about 43% as intense as on Earth. Nuclear systems provide consistent power regardless of distance or sun angle, essential for life support, scientific equipment, and communications. NASA has developed advanced nuclear reactors specifically for space use, compact enough to transport but powerful enough to meet mission needs. These systems also generate heat, useful for maintaining comfortable temperatures during cold Martian nights when temperatures can plunge to 200 degrees below 0 Fahrenheit. On the surface, nuclear power could enable industrial activities, running equipment to extract water and fuel, operating laboratories, maintaining comfortable habitats. The first humans to land on Mars will leave footprints that could last millions of years. Unlike Earth, where wind, rain, and geological processes constantly reshape the surface, Mars is geologically quiet. Its thin atmosphere creates gentle winds that move dust but rarely erase surface features. Rover tracks from missions that landed decades ago remain visible in satellite images. Human footprints, boot treads pressed into ancient Martian soil, might persist longer than any human monument on Earth, becoming the most enduring evidence of our species' existence. These first explorers will know their every step writes history in the red dust, that future generations might visit these sites the way we visit ancient historical places on Earth. The landing site of the first human Mars mission will become sacred ground, preserved and protected. A place where people pause to remember the courage it took to begin something entirely new. Future Mars missions plan to establish a base called Mars Base Alpha. Though still conceptual, designs show a complex of interconnected habitats, laboratories, workshops, greenhouses, and storage facilities. Some structures would be prefabricated on Earth and deployed by robots before humans arrive. Others might be constructed from Martian materials using 3D printing technology. Autonomous machines mixing Martian soil with binders to create concrete. Slowly building protective walls and infrastructure. Solar panel arrays and nuclear reactors would provide power. Rovers, and eventually pressurized ground vehicles, would enable exploration beyond the immediate base area. The base would grow over time as successive missions bring more equipment and supplies, eventually supporting dozens of people living and working on Mars for extended periods. The first base will be modest, focused on survival and scientific research, but it represents humanity's first permanent foothold beyond Earth. The distance to Mars transforms how decisions are made. Astronauts will need to troubleshoot problems with only their training and judgment, handle emergencies knowing expert advice arrives too late to help in urgent moments. This independence brings both capability and quiet solitude. Future Mars crews will be selected partly for their ability to work as a small, self-reliant team, maintaining morale and purpose when Earth feels far away. They'll need resourcefulness and resilience, creativity and calm under pressure. The communication delay doesn't just change operations, it changes the fundamental nature of the mission, transforming astronauts from explorers following ground control's directions into truly independent pioneers. They'll collaborate effectively as a small team, facing challenges together, developing the skills to thrive in isolation while maintaining connection to the human family waiting back home. The inner journey to Mars matters as much as the outer one. Astronauts will spend years in isolation, confined to small spaces with the same handful of people, unable to step outside without a spacesuit, watching Earth become a point of light indistinguishable from stars. Mental health support will be crucial. Regular contact with loved ones despite communication delays, private spaces for solitude, meaningful work that provides purpose, recreational activities to maintain joy and connection. NASA studies how isolated groups interact over long periods, learning from Antarctic winter over crews, submarine sailors, and International Space Station astronauts. They're developing tools for monitoring mental health, interventions when problems arise, and team selection processes that identify people with the right combination of technical skills, emotional resilience, and psychological flexibility. The first Mars crew will be evaluated as much for their ability to maintain harmony and hope as for their technical competence. Asteroid mining remains a promising concept that could eventually provide resources for deep space missions. Though no commercial operations exist yet, several companies continue researching the technologies needed to extract water and metals from near-Earth asteroids. Water from asteroids could be split into hydrogen and oxygen rocket fuel. Metals could be refined and used for construction. For Mars missions, asteroids might someday serve as refueling depots. Spacecraft could stop at an asteroid on the way to Mars, extracting water to replenish fuel supplies. The technology is complex and unproven, but the concept is sound. If successful, asteroid resources could transform space economics, making Mars missions more affordable and sustainable, reducing dependence on Earth's resources, and opening possibilities for industrial activities in space. Future spacecraft will use advanced propulsion systems faster than today's chemical rockets. Ion drives, already used on some robotic missions, accelerate ions to extremely high velocities, providing gentle but continuous thrust that eventually produces higher speeds than traditional rockets. Nuclear thermal propulsion heats propellant using a nuclear reactor, offering better efficiency than chemical rockets. Some researchers explore even more exotic concepts: fusion drives, antimatter propulsion, even theoretical systems that might manipulate space-time itself. While most of these remain speculative, incremental improvements in propulsion could dramatically reduce Mars journey times from 7 months to perhaps 3 or 4 months, reducing astronaut radiation exposure, psychological stress, and mission costs. Every advancement in propulsion technology brings human settlement of the solar system closer. The first Mars explorers might search for signs of ancient life in the planet's rocks and soil. Billions of years ago, Mars was warmer and wetter, with rivers, lakes, and perhaps even an ocean covering much of its northern hemisphere. If life emerged on early Mars, as it did on Earth, evidence might still exist. Fossil microbes in ancient lake beds, chemical signatures in rocks formed in water, organic molecules preserved in Martian minerals. Finding proof that life arose independently on Mars would revolutionize our understanding of biology and the universe. It would suggest life is common in the cosmos rather than a unique accident. Mars missions will include sophisticated laboratories for analyzing samples, searching for the subtle clues that would indicate biological processes rather than pure geology. Terraforming Mars remains a distant possibility, transforming its cold, thin atmosphere into something breathable by humans. Proposed methods include releasing greenhouse gases to warm the planet, melting polar ice caps to release water vapor and carbon dioxide, importing volatile materials from comets or asteroids, using mirrors in orbit to concentrate sunlight on the surface. Over centuries or millennia, these efforts might thicken the atmosphere, warm the climate, and potentially allow liquid water to exist on the surface. Some scientists question whether Mars has enough volatile materials to create a substantial atmosphere. Others wonder about the ethics of deliberately altering an entire planet. But as a long-term vision, terraforming represents humanity's ultimate ambition in space, not just visiting other worlds or building bases on them, but reshaping them to suit human needs. So, yes, these plans for moon bases and Mars missions and asteroid mining are changing how we think about space. For decades, space exploration meant government-funded projects sending a handful of carefully selected people into orbit for brief visits. Now we're discussing permanent settlements, commercial activities, growing human populations living and working beyond Earth. The transition from exploration to colonization represents a fundamental shift in humanity's relationship with space, from visitors to inhabitants, from studying other worlds to living on them. The technology required is mostly understood, though much remains to be refined and tested. The greatest challenges may be human: building sustainable communities in new environments, maintaining social cohesion across vast distances, creating economies that make off-world living practical. Future space travel is emerging from science fiction into planning documents and budgets, and hardware being assembled in factories right now. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the astronauts we send to the heavens, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronauts breathed while looking down at Earth from above. We are all space travelers, flying on a small planet through the galaxy. Now we continue. The human body begins changing within hours of reaching space. Without gravity's constant pull, fluids that normally pool in the legs redistribute upward throughout the body. Astronauts' faces become puffy and their legs thin as blood, and lymph flow toward the head and chest. This fluid shift increases pressure in the skull, pressing on the brain and eyes, causing what NASA calls spaceflight-associated neuroocular syndrome. About 2/3 of International Space Station crew members experience changes to their vision, blurring, far-sightedness, sometimes lasting months or years after returning to Earth. The optic nerve may swell, the eyeball flatten, the retina develops small areas of change. Researchers are still working to understand exactly why this happens and how to prevent it. For Mars missions lasting years, these vision changes could significantly affect crew capability and safety, making this one of NASA's highest priority research areas. Microgravity causes muscles to atrophy rapidly without exercise. On Earth, gravity provides constant resistance. Your muscles work continuously to maintain posture, support your weight, move through space. In orbit, movement requires minimal effort. Without deliberate exercise, astronauts could lose significant muscle mass during long missions, in extreme cases up to 30%, particularly in the legs and back. This isn't just about strength. Muscles help regulate metabolism, support the immune system, protect bones and joints. That's why International Space Station astronauts exercise about 2 hours every day using specially designed equipment, resistance devices that simulate weightlifting, treadmills with harnesses that pull them down against running surfaces, stationary bicycles. Even with intensive exercise, some muscle loss occurs. For Mars missions, maintaining muscle health through the 7-month journey and the return journey presents serious challenges that exercise alone may not fully solve. Bones lose density in space, becoming more fragile over time. On Earth, bones constantly rebuild themselves in response to mechanical stress. When you walk or run, tiny impacts trigger cells to strengthen bone structure. In microgravity, this process falters. Bones release calcium into the bloodstream faster than they rebuild, losing density at rates of roughly 1 to 2% per month in the hip and spine, the bones that normally carry our weight against gravity. The loss continues as long as astronauts remain in space, though it may slow after several months as the body reaches a new equilibrium. After 6 months aboard the International Space Station, some astronauts return with bone density reduced 10 to 15%. It can take months or years for bones to fully recover, and some may never regain their pre-flight density. The heart physically changes in space, adapting to conditions where pumping blood requires less effort. Without gravity pulling blood downward, the heart doesn't work as hard to circulate blood to the brain. Over months, the heart muscle weakens and the organ itself may shrink slightly. Blood volume decreases as the body senses it has more fluid than needed. Cardiovascular fitness declines even with regular exercise. These changes matter most upon return to Earth, when astronauts must suddenly readapt to gravity. Standing quickly can cause dizziness or fainting as the weakened heart struggles to pump blood upward against gravity's pull. Researchers are developing better exercise countermeasures and considering medications that might help maintain heart health during long missions. Space affects the immune system in complex ways that scientists are still unraveling. Some immune responses weaken, wounds heal more slowly, latent viruses can reactivate, susceptibility to infection may increase. At the same time, inflammation markers often rise, suggesting the immune system is working overtime even as specific defensive capabilities decline. Stress from spaceflight, radiation exposure, disrupted sleep patterns, and confined living conditions all impact immune function. Samples from astronauts show changes in immune cell populations and gene expression patterns related to inflammation and cellular stress. For Mars missions, maintaining immune health is essential. No emergency medical evacuation is possible when Earth is months away. Researchers are studying whether certain supplements, medications, or lifestyle interventions might boost immune function in space. Space radiation affects the body in ways scientists are still discovering. Recent research from 2025 reveals that cosmic rays may alter how cells communicate with each other, potentially affecting tissue regeneration and aging processes. Unlike Earth-based radiation that travels in straight lines, space radiation includes heavy ions that create complex patterns of cellular change. Researchers at Duke University and NASA are developing biological countermeasures, medications that might enhance the body's natural repair mechanisms, helping cells recover from exposure during long missions. What happens during multi-year missions to Mars remains unknown. Understanding these effects guides decisions about mission duration, shielding design, and crew health monitoring. Recent research from 2025 shows that astronauts experience measurable brain changes during spaceflight. Brain imaging before and after missions reveals the brain physically shifts upward in the skull as fluid redistribution and microgravity reduce the downward pressure that normally exists. The spaces containing cerebrospinal fluid around the brain expand, particularly the ventricles at the brain's center. Studies show these changes are larger after longer missions. 6-month stays cause more change than 2-week missions, and year-long missions cause even greater shifts. Most effects are temporary, resolving within months after landing, but scientists don't yet know if repeated or very long missions might cause permanent changes. Sleep becomes challenging in space for multiple reasons beyond just excitement. The International Space Station completes an orbit every 90 minutes, meaning crew members experience 16 sunrises and sunsets every 24 hours. This disrupts circadian rhythms, the internal biological clock that normally follows Earth's day-night cycle. Despite scheduled sleep periods and window shades, many astronauts report difficulty sleeping soundly, averaging only about 6 hours per night compared to 7 or 8 on Earth. Contributing factors include noise from fans and equipment, concern about floating into things while sleeping, and the psychological effects of the alien environment. Poor sleep affects performance, mood, and health. For Mars missions, the transit phase might see improved sleep without the rapid day-night cycles. But living on Mars presents its own challenge. The Martian day is 24 hours and 37 minutes long, just different enough from Earth's day to potentially disrupt sleep over time. The psychological experience of viewing Earth from space profoundly affects many astronauts. Called the overview effect, this phenomenon involves sudden, overwhelming feelings of awe, interconnection, and perspective shift. Seeing Earth as a fragile blue marble suspended in cosmic darkness, with paper-thin atmosphere glowing at the edges, can dissolve feelings of division and emphasize humanity's shared vulnerability and common home. Many astronauts report this experience changes them permanently, making them more environmentally conscious, more interested in global cooperation, less concerned with petty conflicts. Some describe it as spiritual regardless of their religious beliefs. But Mars travelers won't have this experience in reverse. Watching Earth shrink away to a point might trigger feelings of isolation rather than connection. NASA screens candidates for psychological resilience, but there's no perfect way to predict how individuals will respond to such profound distance from everything familiar. Time perception changes in the strange environment of space. Without natural day-night cycles, without seasonal changes, without the countless environmental cues that normally help us judge time's passage, astronauts often report feeling disoriented about how long they've been in space or how much time has passed. Moments of high activity fly by while quiet periods drag. The sameness of the environment, the repetitive daily routines, the isolation from Earth's normal pace of life all contribute to this temporal distortion. Some crew members report the initial weeks of a mission feel very long as they adjust to the new environment, but later months pass quickly. For Mars missions lasting years, Maintaining temporal awareness and structure will be important for psychological health. Scheduled activities, celebrations of holidays, and personal milestones. Communication with Earth to stay connected to its rhythm. Recent studies show that even brief spaceflight causes genetic changes. The NASA Twins study, comparing astronaut Scott Kelly after a year in space with his identical twin Mark, who remained on Earth, revealed thousands of genes changed their expression patterns. Telomeres, protective caps on chromosomes, unexpectedly lengthened in space, then rapidly shortened upon return. Many changes reversed within months of landing, but some persisted. A 2025 catalogue of spaceflight biological data, analyzing dozens of astronauts and even 3-day tourist missions, found similar patterns appearing quickly. Inflammation markers rise, immune gene expression shifts, stress response pathways activate. These aren't mutations, but rather changes in how genes function, potentially affecting health and aging. Taste changes in space, with many astronauts reporting foods taste blander than on Earth. The fluid shift that causes facial puffiness also affects nasal passages, creating a stuffy nose sensation that diminishes the sense of smell, which is crucial for taste perception. Additionally, in microgravity, liquids don't drain normally from sinuses and airways, contributing to persistent congestion. Astronauts often prefer spicier, more strongly flavored foods. Hot sauce is extremely popular aboard the International Space Station. This has practical implications beyond just meal enjoyment. Good tasting food improves morale and ensures adequate nutrition, important for maintaining health and energy over long missions. But for Mars missions with no resupply, food variety becomes limited, and the taste changes persist indefinitely. Growing fresh food helps both nutritionally and psychologically, providing variety and the satisfaction of harvesting something that tastes truly fresh. Balance and coordination take days or weeks to fully readjust after returning from space. Without gravity, the vestibular system, inner ear structures that sense orientation and motion, receives confusing signals. On Earth, when you tilt your head, tiny crystals in your inner ear shift, triggering nerves that tell your brain which way is down. In space, these crystals float freely, providing no useful information. The brain learns to ignore these signals and rely more on vision and proprioception, sensing body position through muscles and joints. Upon returning to Earth, astronauts must relearn to trust their vestibular system. Many experience dizziness, spatial disorientation, and balance problems initially. Walking feels strange, as if the floor is tilting unexpectedly. Most people readapt within a few days, though some effects persist for weeks. Social dynamics in isolated, confined environments require careful management. Research from Antarctic stations, submarines, and the International Space Station reveals common patterns. Crew members pass through phases of adjustment, from initial excitement through mid-mission doldrums to end-of-mission anticipation. Conflicts can arise from personality clashes, cultural differences, or simply fatigue from living in close quarters. Small annoyances can escalate into serious problems when there's no escape or privacy. Successful missions require crew members with strong interpersonal skills, emotional intelligence, ability to communicate clearly and resolve conflicts respectfully. NASA carefully selects teams based on psychological compatibility, not just technical skills. For Mars missions, lasting up to 3 years with possibly just 4 to 6 people, social cohesion becomes crucial. Despite all these challenges, humans are remarkably adaptable. Astronauts aboard the International Space Station develop new ways of moving in 3 dimensions. Learning to fly through modules with precise control, they adjust to eating floating food, to sleeping while floating, to seeing Earth continually pass by below. What initially seems alien gradually becomes normal. a remarkable demonstration of human neurological plasticity and resilience. The body finds new equilibriums for systems that evolved under gravity's influence. The mind adjusts to extraordinary circumstances, maintaining function and even finding joy in the strange environment of space. This adaptability gives hope for Mars missions. Humans have consistently surprised themselves with their ability to thrive in environments that seemed impossible. Space is more extreme than any Earth environment. Yet astronauts not only survive, but accomplish meaningful work, maintain their humanity, and often return wanting to go back. You're still here, still awake, still drifting with us through these stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I and everyone listening in the quiet dark, floating through facts like asteroids drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. Evolution prepared humans for adaptation in ways we're only beginning to understand. Our ancestors survived by spreading into new environments, from African savannas to frozen tundras, from coastal regions to high mountains. Each environment presented unique challenges, requiring physical and behavioral adjustments. Some populations evolved genetic changes over generations: tolerance for high-altitude thin air, ability to digest new foods, resistance to local diseases. But beyond genetic evolution, humans possess remarkable phenotypic plasticity. The same genes produce different outcomes depending on environmental conditions. Your body can adjust blood chemistry for altitude, strengthen bones in response to physical stress, alter immune function based on local pathogens encountered. These capabilities now serve us in the most alien environment we've encountered: space itself. The human brain's neuroplasticity allows rapid adaptation to new sensory environments. When astronauts first enter space, their brains receive contradictory signals. Eyes report one thing, inner ears another, proprioception something else. Initially, this causes space motion sickness, disorientation, and confusion. But within days, the brain learns new patterns, reweights different sensory inputs, and constructs a new internal model of the environment. Astronauts report a sudden shift when space stops feeling wrong and starts feeling normal. This same neuroplasticity allows adaptation to Mars's partial gravity, to living in confined habitats, to the altered sensory environment of wearing spacesuits for extended periods. The brain doesn't just passively receive reality, it actively constructs your experience of the world based on available information. Humans excel at creating artificial environments that meet our needs. We don't adapt to winter by growing thick fur. We build heated shelter and wear appropriate clothing. We don't adapt to underwater environments by developing gills. We bring air supplies. This ability to modify environments rather than waiting for biological evolution has allowed humans to inhabit nearly every Earth environment. Space simply extends this pattern. We can't breathe vacuum, so we bring breathable atmosphere. We can't survive radiation, so we build shielding. We need gravity for health, so we might create artificial gravity through rotation. This technological adaptability complements our biological adaptability. Together, they suggest humans might eventually thrive in space, not by becoming biologically different, but by cleverly engineering environments that provide what our bodies need. Psychological resilience varies among individuals, but can be strengthened through training and practice. NASA has learned that certain traits predict success in extreme environments: emotional stability, high tolerance for ambiguity and uncertainty, ability to maintain motivation during boring or difficult periods, good interpersonal skills, capacity for delayed gratification. They screen candidates for these traits and strengthen them through training. Astronauts practice in simulated missions, learning to handle equipment failures, interpersonal conflicts, and boring routine with equal composure. They develop coping strategies, exercise routines, hobbies, communication with loved ones, mindfulness techniques. This preparation helps, though no simulation perfectly captures the reality of being millions of miles from help. Yet time and again, humans facing extreme challenges discover inner resources they didn't know they possessed. Cultural evolution happens much faster than biological evolution, allowing rapid transmission of adaptive strategies. When one astronaut discovers a better way to perform a task in microgravity, they can teach others immediately. Knowledge accumulates. Each mission builds on lessons learned from previous ones, developing informal techniques and best practices. The International Space Station has been continuously inhabited for 25 years as of November 2025, creating an accumulated knowledge base about living in space that no single person could develop alone. This cultural transmission will be crucial for Mars missions. Early explorers will establish practices, solve problems, discover what works and what doesn't. Subsequent missions will build on this foundation, inheriting a cultural tradition of Mars living that makes each successive group's adaptation easier. The human need for meaning and purpose drives adaptation to difficult circumstances. Viktor Frankl, surviving Nazi concentration camps, observed that those who maintained purpose, caring for others, working toward a goal, holding on to values, were more likely to survive than those without meaning. Astronauts consistently report that the mission's importance sustains them through challenges, advancing human knowledge, preparing for future explorers, representing humanity's highest aspirations. For Mars pioneers, this sense of purpose will be essential. They're not just enduring difficulties, they're expanding human civilization, proving our species can become multiplanetary. This purpose provides psychological resilience during hardship. Even in difficult moments, they can remember why they're there, what their sacrifice means, how their actions echo through history. Physical exercise serves as both countermeasure and coping mechanism during spaceflight. Beyond maintaining muscle and bone health, exercise provides stress relief, mood regulation, sense of accomplishment, structured time in a day that might otherwise blur together. Astronauts report that their daily exercise sessions help maintain psychological well-being as much as physical health. The endorphins released during exercise improve mood. The sense of pushing against resistance, of becoming stronger, contrasts with the helplessness that might otherwise arise from living in an environment where survival depends entirely on technology and outside support. Exercise represents control, agency, self-determination, choosing to improve yourself despite circumstances. Connection with loved ones back on Earth provides crucial psychological support during space missions. Regular communication, video calls, emails, even simple photos, helps astronauts feel less isolated, maintains important relationships, reminds them they're part of something larger than the mission. They celebrate birthdays and anniversaries with their families, albeit through video screens and time delays. They share everyday moments, keeping their lives on Earth alive in their minds. For Mars missions, communication delays will complicate this. Conversations will occur through recorded messages rather than real-time exchanges, turning dialogue into a slow exchange of monologues. Yet even with delays, maintaining these connections matters immensely. Knowing people back home are thinking about you makes the isolation more bearable. Humans create beauty and meaning even in the harshest environments. Astronauts aboard the International Space Station play musical instruments, create art, take photographs of Earth's stunning vistas. They celebrate holidays and birthdays, share meals together, tell stories and jokes. These activities might seem frivolous compared to critical systems maintenance and scientific research, but they're essential for maintaining humanity in an inhuman environment. Mars missions will need to incorporate opportunities for creative expression, celebration, play, and beauty. Long-duration spaceflight isn't just about survival. It's about living well, maintaining joy and wonder despite challenges. So why are humans capable of adapting to space? Perhaps because nothing in our evolutionary history prepared us to accept limits. Our ancestors looked at oceans and built boats. They saw mountains and climbed them. They imagined flight and eventually achieved it. Now we look at Mars and dream of walking its surface. This drive to explore, to extend our reach, to overcome obstacles seems fundamental to human nature. The challenges of space are significant, but they're not fundamentally different from challenges humans have always faced. Hostile environments, scarce resources, isolation, danger. We've developed biological adaptability, technological capability, psychological resilience, and social cooperation specifically to overcome such challenges. The body and mind that carried us from African plains to Antarctic ice to ocean depths can carry us to Mars and beyond. We're built for this journey, even if we didn't know it until now. Breathe deeply and imagine. Space is never truly empty. Even in the vast darkness between stars, there are particles, energy, invisible fields flowing through the void. The space around you right now isn't empty either. Electromagnetic waves, air molecules dancing, possibilities floating in quantum uncertainty. Let each breath guide you to realize, time is yours, a separate stream that only you are living. While the vast universe continues to spin, expand, change, this second you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe. And we continue drifting. Becoming a spacefaring civilization fundamentally changes how we see ourselves. For all of human history until 1961, every person who ever lived was born, lived, and died on Earth's surface. Now hundreds of people have traveled to space, and a few have lived there for over a year at a time. This shift from Earth-bound to occasionally space venturing represents a change as significant as when our ancestors left the trees for the savannas, or when they first crossed oceans to reach new continents. We're no longer a species confined to one environment, dependent entirely on one planet's resources and weather. We're learning to live beyond the cradle that nurtured our evolution, carrying our bubble of life into lifeless regions. Space travel requires cooperation across nations and cultures in unprecedented ways. The International Space Station involves 15 countries working together: United States, Russia, Japan, Canada, and 11 European nations. Astronauts from different countries live together in space, dependent on each other's competence and goodwill for survival. The station itself blends technologies from multiple nations. Russian modules docked to American ones, European service modules, Japanese laboratories. This cooperation persists even when relationships on Earth grow tense. Political conflicts that might otherwise escalate stop at the edge of space, where common dependence on shared systems creates practical necessity for partnership. Mars missions will likely require similar international cooperation. No single nation can easily afford or execute such ambitious plans alone. The economic implications of space colonization extend far beyond the initial missions. Access to space resources, minerals from asteroids, energy from space-based solar arrays, manufacturing in microgravity that produces unique materials impossible to make on Earth, could generate enormous wealth. This potential drives private companies like SpaceX, Blue Origin, and others investing billions in space infrastructure. But space economics also raises questions about ownership and equity. Who owns asteroid resources? Can nations or companies claim territory on Mars or the Moon? Early space treaties declare space the province of all mankind, but interpreting this for commercial activity remains contentious. How benefits from space are distributed will shape humanity's future in profound ways. Mars settlements might eventually declare independence from Earth, creating humanity's first off-world political entities. Communication delays make real-time governance from Earth impractical. Mars colonists will need to make their own decisions about local issues, resource allocation, dispute resolution, community organization. Over time, their interests might diverge from Earth's. They might develop distinct cultural identities shaped by Mars's unique environment and challenges. Some envision Mars colonies eventually becoming self-governing, perhaps following democratic principles, perhaps developing new forms of governance suited to their circumstances. These questions might sound like science fiction, but they'll become real as soon as significant populations live permanently off Earth. The concept of home shifts when you can see your planet as a distant point of light. Astronauts describe profound attachment to Earth after seeing it from space. That fragile blue marble containing everyone they've ever known, every place they've ever been. All of human history and culture, Earth becomes precious in a way that's hard to explain to those who've only seen it from ground level. But for Mars colonists, this might reverse. Children born on Mars might see Earth as the distant alien place where their grandparents came from. Mars would be home, the red soil under their feet, the butterscotch sky overhead, the habitat modules where they sleep and work. Home becomes not a specific planet, but wherever you belong, where your community thrives, where familiar rhythms and patterns provide comfort and meaning. Language might evolve differently in space environments, developing new words and idioms for experiences unique to space living. Just as seafaring cultures developed rich vocabularies around ships and navigation, space cultures will create terms for their environment. Already, astronauts use jargon incomprehensible to outsiders, discussing phasing, burns, insertion, rendezvous. Future Mars colonists might develop entirely new words for Martian-specific concepts, adopt metaphors based on red dust storms instead of rain, measure time by Martian sols instead of Earth days. Distant colonies might develop distinct dialects or even languages over generations, particularly if communication with Earth becomes infrequent. Language shapes thought, and new languages might shape new ways of understanding the universe. We don't yet know if families can grow naturally in reduced gravity. Animal studies hint at possible differences in development, and researchers are carefully studying how the body's most delicate processes adapt to new environments. Before committing to permanent Mars colonies, we need to understand whether healthy children can be born and raised there. If Mars gravity proves insufficient for normal human development, this might limit settlement to scientific outposts with rotating crews, rather than true colonies, with families and children. Or perhaps children born on Mars would develop differently, taller and thinner in reduced gravity, perhaps with different bone and muscle development. These questions remain open, inviting future scientists to discover whether children might one day be born under different skies. Cultural heritage preservation becomes complex when humanity splits across multiple worlds. If Mars colonies develop distinct cultures, how do they maintain connection to Earth's history and traditions? Do they celebrate Earth holidays, study Earth geography and ecosystems their children will never experience? Or do they create new holidays commemorating Mars events, new traditions suited to Martian seasons and circumstances? How do you preserve 7,000 years of human civilization and culture for a generation growing up where none of it physically exists? Digital archives help, but they're not the same as walking through ancient cities or seeing original artwork. Eventually, human culture might fragment into Earth culture and Mars culture, and perhaps others as humanity spreads farther. Religion and spirituality face interesting questions in the context of space colonization. How do Earth-centered religious traditions adapt when adherents live on other worlds? What's the Qibla direction for Muslim prayers on Mars, toward Earth where Mecca exists, or some other solution? How do you observe Sabbaths or religious holidays based on Earth's 7-day week and seasonal calendar, when living on a world with different day lengths and no seasons as Earth knows them? Some theologians and religious leaders have begun contemplating these questions, but definitive answers await actual off-world communities facing these practical challenges. Space might also inspire new forms of spirituality based on cosmic perspective, reverence for the universe's vastness, appreciation for life's rarity and preciousness. The legal framework for space activity remains underdeveloped and contested. The Outer Space Treaty of 1967, signed during the Cold War, established that space belongs to all humanity, that no nation can claim territory on celestial bodies, that space should be used for peaceful purposes. But this treaty predates modern space commercialization and offers little guidance for companies mining asteroids, individuals buying passage to orbit, or nations establishing lunar bases. When do temporary research stations become permanent territorial claims? Who has rights to resources extracted from asteroids or Mars? As space activity increases, pressure will grow to update legal frameworks, but achieving agreement among nations with competing interests will be challenging. Education systems will need fundamental revision for children growing up on Mars. What do Martian students need to learn? Earth geography might be interesting history, but Martian geography is practical survival knowledge. Biology based on terrestrial life forms is heritage. But understanding how Earth organisms adapt to Mars environments is essential. Mathematics and physics remain universal, though examples might differ. Orbital mechanics and rocket equations become more relevant than phenomena experienced only in Earth's gravity. Literature, art, music from Earth remain part of human heritage worth teaching. But Martian students might also create their own cultural expressions. Healthcare in space settlements requires self-sufficiency impossible to achieve initially. Earth-based medicine relies on vast supply chains, pharmaceutical factories, medical equipment manufacturers, specialized practitioners and facilities. A Mars colony must handle medical emergencies with only the resources available locally. No medical evacuation to specialized hospitals. No overnight delivery of urgently needed medications. Early colonies will need doctor astronauts with extremely broad training, capable of handling everything from routine illnesses to surgical emergencies. They'll need laboratories to produce common medications, 3D printers to fabricate medical devices, telemedicine connections to Earth specialists for guidance despite communication delays. The cycle of life and letting go takes on new meaning in space. When someone's journey ends far from Earth, new traditions will emerge. Perhaps a quiet ceremony under alien stars. Perhaps returning to the cosmos that created us. These are questions that invite reflection rather than worry, reminding us that wherever we go, we carry our deepest human needs for meaning and remembrance. The first off-world ceremonies might blend traditions from many Earth cultures, creating something new that honors the past while accepting the unique circumstances of life beyond our homeworld. Over time, Mars colonists might develop their own ways of honoring those who've passed, rituals suited to their environment and values. The psychological impact of living under a limited sky, where you can't simply step outside and breathe free air, might be Mars colonization's greatest challenge. Humans evolved in open environments with vast horizons, natural light, fresh air, and weather, rain, wind, the warm sun on your skin. Mars offers none of this naturally. Stepping outside requires donning a spacesuit, and then you're still enclosed, breathing recycled air, seeing through a faceplate. Many colonists might spend most of their time in underground or domed habitats, with limited views of the Martian surface. Habitat designers will need to address these psychological needs. Large windows, interior gardens, full-spectrum lighting that mimics natural sun. Perhaps high ceilings and architectural features that create feelings of spaciousness despite physical limitations. The concept of seasons differs fundamentally on Mars, despite the planet having axial tilt that creates seasonal variations. A Martian year lasts 687 Earth days, almost twice as long. Each season stretches for months. Spring and summer in the southern hemisphere last longer than in the north due to Mars's elliptical orbit. Global dust storms can occur during certain seasons, darkening skies and reducing solar power generation. Temperature variations are extreme. Winter nights can reach 200 degrees below 0 Fahrenheit, while summer days might briefly reach 70 degrees at the equator. Colonists will need to plan activities around these cycles, growing food during certain seasons, conserving power during dust storms, perhaps timing exploration expeditions for favorable conditions. Earth has weathered many changes over billions of years, and life has proven remarkably resilient. Still, having a second home among the stars provides gentle reassurance, like keeping a spare key with a trusted friend. Not because we expect to need it, but because wisdom suggests we might, someday, be glad we prepared. Space colonization driven by this logic isn't escapism, it's prudent risk management at a species level, and the effort to establish Mars colonies might help Earth too. Technologies developed for off-world living could address Earth challenges. Renewed sense of common purpose might reduce conflicts. Cosmic perspective might inspire better stewardship of our home world. The timeline for Mars colonization extends over generations, not years. Initial missions establish basic infrastructure and prove survival is possible. Subsequent missions expand capabilities, bringing more supplies and equipment, perhaps more people. Early decades might see only small scientific outposts with rotating crews. True colonization, families settling permanently, children born on Mars, self-sufficient communities, likely won't begin until mid-century or later. Growing to hundreds or thousands of people might take a century. This multi-generational timescale means current planners won't see the vision fulfilled. They're laying foundations for a future they'll never witness, working toward goals that benefit descendants they'll never meet. Identity questions arise for children born on Mars, members of the first genuinely multiplanetary generation. Are they Martian or human or both? Do they belong to Earth nations their parents came from, or are they something new? They'll grow up speaking of Earth as foreigners speak of distant homelands their grandparents left. Important to their heritage, but not their lived experience. Earth might seem as mythical to them as ancient Babylon or Athens seems to us. Historical places they've studied but never visited. Yet they're still human, still carry the genetic and cultural heritage of Earth's civilizations. This generation will need to navigate dual identity, inheritors of Earth's cultures and pioneers of new Martian society. The experience of experiencing red planet nature, dust devils swirling across plains, morning frost sublimating as sun rises, vast canyon systems dwarfing anything on Earth, might inspire new forms of art and appreciation. Just as Earth's nature inspired poetry, painting, music, and philosophy across cultures, Martian landscapes might inspire uniquely Martian aesthetic sensibilities. The subtle color variations in rock layers, the delicate patterns frost creates, the play of light through dust-filled air during storms, these might be beautiful to those who learn to see them. Early colonists will photograph and paint and write about their new world, sharing these perspectives with Earth. The philosophical question, why go to Mars, receives different answers depending on whom you ask. Scientists value Mars for understanding planetary formation, searching for life, and studying geology and climate. Engineers see challenges to overcome and technologies to develop. Entrepreneurs envision new industries and markets. Dreamers imagine the adventure and frontier spirit. Pragmatists point to reducing existential risk and accessing space resources. All these motivations are valid, and different motivations might drive different stages of colonization. Ultimately, asking, why go to Mars might be like asking, why did humans settle every continent? The answer isn't one simple reason, but a complex mix of curiosity, opportunity, necessity, and the fundamental drive to explore. Communication technology will be essential infrastructure for Mars colonies, maintaining connection to Earth and enabling coordination across spread-out settlements. Mars and Earth regularly move out of direct line of sight from each other, requiring relay satellites at strategic points to maintain contact. Communication bandwidth will be limited. Sending high-resolution video is much harder across interplanetary distances than across terrestrial internet. Yet colonists will need robust communication for psychological well-being, scientific collaboration, commercial activities, and emergency coordination. Developing this infrastructure is expensive and complex, but essential. The concept of nationality becomes complicated when people live permanently off-world. Current space law bases jurisdiction on nationality. Astronauts remain subject to their home country's laws in space, but Mars colonists might spend decades off Earth. Their children might never visit Earth. Do they remain citizens of countries that are just names to them? Can Earth nations enforce laws across interplanetary distances? Mars settlements might eventually claim sovereignty, but under what authority? Who grants recognition? These aren't just legal technicalities. They affect daily life. What legal protections do colonists have? What obligations? Who resolves disputes? Resource independence remains a long-term goal rather than initial reality for Mars settlements. Early colonies will depend heavily on supplies from Earth, spare parts, specialized equipment, food variety, medications, countless items too complex to manufacture locally. But each item shipped from Earth is expensive, and supply runs occur only every 26 months. So colonies will work towards self-sufficiency incrementally. First producing basic necessities like water and oxygen, then growing food, eventually manufacturing simple items, slowly building industrial capacity. Complete independence might never happen. Some specialized products might always come from Earth, just as remote Earth locations import certain goods despite local production of basics. The question of who gets to go to Mars raises thorny issues of fairness and selection. Should opportunities go to the wealthy who can afford passage? To the most qualified candidates chosen through competitive selection? Should nations control access, or should it be privatized? If settling Mars benefits all humanity, should people from all nations have equal opportunity? How do you balance competence requirements, ensuring settlers have skills colonies need, against diversity goals? These questions have no simple answers and mirror historical patterns where economic factors, political power, and social connections determined who could settle new lands. So, what does it mean to be spacefaring? It means accepting that Earth isn't the only place humans can live, that our species' future extends beyond our home planet. It means willingness to face extraordinary challenges for goals that benefit future generations. It means reimagining human civilization as something that can exist across multiple worlds, maintaining connection despite distances that dwarf anything Earth-bound societies ever navigated. It means technical competence, developing technologies that let humans survive in environments evolution never prepared us for. It means social flexibility, creating new forms of governance, culture, and community suited to unprecedented circumstances. Becoming spacefaring is more than technological achievement. It's psychological and cultural transformation, expanding our identity from residents of one planet to citizens of the cosmos. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spacecraft orbit Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. All are circles, cycles, endless orbits. Like your breath, inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order. like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. Here's something profound that might shift your perspective. You're already a space traveler. Earth isn't standing still. It's a spacecraft carrying you through the cosmos at tremendous velocity. We orbit the Sun at 67,000 miles per hour, while the Sun itself travels through the galaxy at over 500,000 miles per hour. While our galaxy moves through space at more than 1 million miles per hour. Every moment, you're traveling vast distances through the universe. You just don't feel it because everything moves together. Earth provides everything a spacecraft needs. It generates its own magnetic field that shields us from radiation. Its atmosphere gives us air to breathe and burns up incoming meteorites. Oceans and weather systems regulate temperature. Plant life recycles carbon dioxide into oxygen. All of this happens automatically, maintaining perfect balance. We call it nature, but it's really the life support system of our planetary spacecraft, working flawlessly for billions of years. The pale blue dot photograph taken by Voyager 1 from 4 billion miles away shows Earth as a tiny point of light, barely visible against the vastness of space. Carl Sagan reflected on this image, noting that everything we've ever known exists on that pale blue dot, all of human history. Every person who's ever lived, every civilization that's risen and fallen. Seeing Earth this way reminds us we're already cosmic citizens, passengers on a small world journey through infinite space. When astronauts return from space, they describe Earth as their true spaceship. They've flown on vehicles humans built, impressive engineering achievements, but then they see Earth, this impossibly complex, self-sustaining, beautiful world, and realize no spacecraft we'll ever build can match the elegance of the one we're already aboard. Earth is the original spaceship, and we're all astronauts, whether we acknowledge it or not. The elements in your body were forged in stars. Hydrogen from the Big Bang. Heavier elements created in stellar cores over billions of years. When massive stars exploded as supernovae, they scattered these elements through space. Gravity eventually gathered them into new stars and planets, including Earth. Your body is literally made of stardust, ancient atoms that traveled through space long before Earth existed. You carry the cosmos within you. Looking at the stars on a clear night connects you across time and space. The light you see left those distant suns years, centuries, or even millennia ago. Ancient photons, traveling through darkness for eons, complete their journey in your eyes. This moment of seeing is the universe experiencing itself through you. Each star you observe is a sun, perhaps with worlds of its own, and your awareness of them creates a thread of connection spanning unimaginable distances. There's poetry in the fact that building spaceships to leave Earth is really just learning to construct temporary versions of what Earth does naturally. We're taking the lessons Earth taught us about sustaining life and trying to apply them artificially. Every spacecraft is a small, imperfect imitation of our home planet. In trying to leave Earth, we're discovering what makes it so special, so perfectly suited to nurturing life. The Moon, our closest neighbor in space, has traveled with Earth for billions of years. It's more than a satellite. It's our companion on this cosmic journey. Its gravity stabilizes Earth's tilt, maintaining climate stability that made complex life possible. The Moon affects ocean tides, which influenced life's evolution. We've never truly traveled alone. Our planetary system includes partners, each playing roles in the ongoing story of life. When we talk about exploring space, we're really talking about exploring ourselves. How do humans respond to isolation? What do we need to thrive? What matters enough that we'd risk everything? What kind of society do we want to build? Space exploration asks these questions in environments that strip away assumptions, forcing us to consciously decide what we value, what we'll sacrifice for, what we want to become. The journey outward is also a journey inward. Future humans living on Mars will still look up at Earth in their night sky. It will appear as a blue star, sometimes visible near the sun, sometimes on the opposite side of the sky. They'll know billions of people live on that distant point of light. They'll feel the same cosmic loneliness and connection that we feel looking at stars. The distances between humans might grow, but the bonds that define us remain. The universe is mostly empty space, yet here we are, matter organized into structures complex enough to contemplate the universe itself. Life is incredibly rare, consciousness even rarer. The fact that we exist at all, that we can wonder about stars and plan journeys to other worlds, represents something precious beyond measure. Every human, every living thing on Earth participates in this unlikely cosmic achievement. Perhaps the purpose of becoming spacefaring isn't really about space at all. It's about growth, pushing past limitations, discovering capabilities we didn't know we possessed, proving that difficult things are achievable when we work together. It's about perspective, seeing ourselves and our world in cosmic context. It's about hope, believing tomorrow can be better, that human potential hasn't reached its limits. These lessons matter whether we settle Mars or not. There's comfort in knowing Earth will continue its journey with or without us. The planet has survived asteroid impacts, ice ages, mass extinctions. It hosted life for billions of years before humans, and it might host life billions of years after we're gone. We're not Earth's purpose. We're just passengers currently aboard. This realization can be humbling, but also freeing. We can relax our grip, understanding we're part of something larger and older than ourselves. Every night, the stars wheel overhead just as they did for our ancestors 1,000 generations ago. The same stars they wondered about, told stories about, navigated by. We're connected to them through this shared experience of looking up and wondering what's out there. Now we're beginning to answer questions they could only imagine. But the wonder remains constant, linking past and future in this present moment. The Voyager spacecraft, both launched in 1977, are now beyond the sun's influence, traveling through interstellar space. They carry golden records with sounds and images from Earth, greetings in many languages, music from different cultures, photographs of human life. These might be the last remnants of humanity to survive, drifting through space long after Earth and Sun have vanished. We've already sent messages to the cosmos about who we are. The oxygen you breathe was created by plants and ocean algae over millions of years. Each molecule has cycled through countless living beings before reaching your lungs. This continuous exchange connects you to forests you'll never see, oceans you'll never visit, and generations of life stretching back through deep time. Every breath links you to the vast web of life on our planetary spacecraft. The question isn't really whether humans will become spacefaring. It's what kind of spacefaring civilization we'll become. Will we carry our best qualities forward? Curiosity, cooperation, compassion, or will we repeat our worst mistakes in new environments? The answer depends on choices we make now, on values we prioritize, on the vision we hold for humanity's future. Space doesn't determine our character. We do. Sometimes the most important journeys aren't measured in distance. A journey inward can be as profound as a journey to Mars. Understanding yourself, finding peace, connecting meaningfully with others. These explorations matter as much as exploring other worlds. Perhaps becoming spacefaring externally requires also becoming spacefaring internally, expanding our inner worlds to match our outer ambitions. The ancient philosophers looked at stars and felt small, awed by the universe's vastness. We still feel that awe, but we've added something new: agency. We're not just observers wondering about those distant lights. We're preparing to visit them, to carry human consciousness out into that vastness. We've gone from asking what's out there to saying we're coming to find out. That shift from passive wonder to active exploration defines this moment in human history. In trying to understand how to live on Mars, We're really learning to be better stewards of Earth. Closed-loop life support, efficient resource use, sustainable energy. These aren't just space technologies. They're lessons about living sustainably anywhere. Perhaps the drive to colonize other worlds will teach us how to better inhabit our own. The same systems thinking required for Mars bases applies to Earth's ecosystems. The timeline of the universe is incomprehensibly vast. The universe is 13.8 billion years old. Earth formed 4.5 billion years ago. Humans have existed for only about 300,000 years. Civilization for about 10,000. We're the newest arrivals, just beginning our story in a cosmos that's ancient beyond imagining. Yet we're here now, conscious and capable, able to leave marks on the universe that might outlast stars. Sometimes the simplest truth is the most profound. You're alive. Right now, in this moment, you exist. Countless improbable events had to occur for you to be here. Your parents meeting, their parents meeting, back through all of history, all the way to Earth's formation, to the stars that created the atoms in your body. Against all odds, here you are, conscious and aware, able to contemplate existence itself. That's already miraculous, regardless of whether humans ever reach Mars. The boundary between Earth and space exists more in our minds than in reality. Our atmosphere doesn't end abruptly. It gradually thins, merging with the solar wind and cosmic particles flowing past. We exist within space, protected by delicate barriers, not separate from it. Earth's magnetic field extends thousands of miles out, interacting with particles from the sun to create auroras. Learning this dissolves the false distinction between here and out there. It's all one continuum, and we're part of it. What if becoming spacefaring isn't about leaving Earth behind, but about expanding what home means? Earth remains our home, our origin, the place that nurtured our development. But home can grow to include the Moon, Mars, the asteroids, eventually other stars. Not replacing our first home, but extending our sense of belonging to embrace more of the cosmos. Home becomes wherever humans create meaning, build communities, tell stories, look out at stars and feel connection. So here's the final truth that brings everything together. You don't need to travel to space to be a space traveler. You already are one. Earth is your spacecraft, the sun your star, the galaxy your neighborhood. Every breath you take, every heartbeat, every thought occurs during a cosmic journey that started 13.8 billion years ago and continues forward into an unknowable future. Mars missions, space stations, moon bases. These are just humans becoming conscious of what we've always been, cosmic beings, products of stars and time and unimaginable processes, temporarily gathered into conscious form, aware enough to wonder about our place in the universe. That awareness, that capacity for wonder and curiosity and the drive to understand, that's what makes us human. That's what makes us explorers. We're already home, already traveling, already part of the cosmos. We're just learning to recognize it. Welcome home, traveler. You've been journeying through the stars your entire life. And so, our quiet journey through space travel comes to a gentle close. We've traveled from spacecraft being assembled in Florida to human minds adapting to alien environments. From the challenges of living beyond Earth to the profound truth that we're already cosmic travelers. From Artemis astronauts preparing for the moon to the philosophical questions of what home means. We've glimpsed how space exploration is both practical challenge and spiritual journey, pushing technological boundaries while expanding our understanding of what it means to be human. Space travel reminds us that everything is connected. The atoms in spacecraft came from ancient stars. The drive to explore comes from curiosity that evolved on Earth. The courage to venture into darkness reflects the same spirit that carried our ancestors across oceans and continents. Much of the most important work happens in silence. Engineers solving problems, astronauts floating through station modules, Earth continuing its ancient orbit while carrying us all forward. Without wonder, without curiosity, without the willingness to reach beyond what's comfortable, we remain confined not by gravity, but by lack of imagination. By pausing to notice, we glimpse the extraordinary truth that exploration isn't about leaving Earth behind, but about recognizing we're already on the grandest journey imaginable. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about the unity of every atom in a black hole, where all boundaries dissolve, light, matter, time, all becoming one. You too can dissolve into sleep like that. No boundaries left between you and rest. Think about consciousness itself, yours, mine, everyone listening, all awareness everywhere, perhaps all connected in ways we don't yet understand. You are not alone in the universe of minds. Let your entire being dissolve into the ocean of consciousness, into dreamless rest, into the space before thought. Prepare for deep sleep, no boundaries left, only peace. If this gentle journey through the cosmos brought you peace, perhaps share it softly with someone else searching for stillness. One quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of space and stars and distant worlds to fade now, like morning mist dissolving in sunlight, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gravity is finally allowed to fully embrace you. If sleep comes, let it carry you like a spacecraft drifting through quiet darkness, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the spacecraft will still be there, preparing for launch. Tomorrow, Mars will still circle the sun, waiting for human footsteps on red soil. Tomorrow, Earth will continue its ancient journey through space, carrying all of us forward. But tonight belongs to stillness. Rest well, sleepy traveler. And remember, you don't need a spacecraft to journey through the cosmos. You're already aboard the greatest ship ever built, traveling through infinite space at incredible speed, warm and safe and held by gravity's gentle embrace. Fall asleep to gentle facts. Good night.